Okay. Well, hello, everybody. Thank you very much for the chance to speak here. Let me just adjust. Yeah, there we go. I'm not sure how these lectures have gone in the last week. I kind of much prefer to give lectures face to face. It turns out that I caught COVID, so just as well that I'm not there. And apologies if I do some coughing, but nothing serious, but in my end. But it sometimes can be bad if it sounds worse than it is on a microphone. Please, I don't know what the protocol has been last week, but please ask questions during the presentation. Don't wait till the end, because I see we have 3 75-minute windows, and I'll leave space for questions at the end as well. But what usually happens is that by the end, people are tired, and normally a question is normally most effective if it's fresh, because whatever it was that was confusing, you can basically fix it when the question arises rather than waiting for a long time. So please do interrupt me. I won't be able to see the chat very well as I'm talking, so maybe one of the organizers could let me know if there's something in the chat I should be paying attention to. That would be good if possible. Okay. So my mandate is to effective field theories and cosmology. And my understanding is that the audience, you are all particle physicists for the most part. And that this is a school, not a seminar. And so this kind of breaks, and I have 3 lectures to work with. And so the topic kind of breaks up nicely into 3 topics. I'm not quite sure how fast I'll be going through things. So how they will divide up by the days, I'm not completely sure. But the story is actually partly an effective field theory story and partly a cosmology story. There, for those that are not doing cosmology, most in particle physics have an aspect of cosmology in what they do, largely because many of the clues for the breakdown of the standard model are coming from cosmology. But if you haven't been following cosmology, it's been actually fascinating, the progress that has been made since it became a precision science. And this, with the discovery with the precise measurements of the microwave background, things have really changed in the way that cosmology is done. It used to be that you could just make things up, and now it really is a precision science. And part of that story is a story of the way that we often learn cosmology, and I'll kind of remind you a little bit of it in these lectures, is we have the story of the expanding universe, but really that's the old school story of the expanding universe. The modern cosmology is all about deviations from the standard expanding universe, because that's the story of structure formation. So how do we see in the very remote past, the universe is very smooth, but we also see galaxies around us now. Where do they come from? And that description of that, the amplification of primordial fluctuations by gravity, is a beautiful story. And it leads to I'll be talking about it because it leads to the central theme of these lectures. And the picture that is emerging is that much of what you see about the distribution of matter in the universe is consistent with the growth of structures from initially small amplitudes under the amplification of gravity. But it also requires an initial spectrum of fluctuations to exist when you extrapolate back in time. And a question arises as to why, what the properties of those primordial fluctuations are. And what's emerged is that they seem to be well described by quantum fluctuations that have been spread across the sky. And so if that's true, and that seems to be the leading proposal, we're seeing the first examples of quantum physics gravitating. It's not a hypothetical, it's something which is claimed to have been actually observed in the sky. And if that's true, and it seems to be true, then it behooves us to understand we can no longer afford to just say, well, quantum gravity is hard. We don't understand what the quantum errors are in gravity. we really have to understand how to make quantum predictions with gravity. And the good news is that we can. And effective field theories are the tool. And so the case I'm going to be making is that where we are now in cosmology and the interface between cosmology and astroparticle physics is that there seems to be good evidence that quantum fluctuations are playing an important role, and how they gravitate is playing an important role in our picture of the universe. And so being able to integrate our quantum understanding with our gravity understanding is no longer just a luxury, it's a necessity, because we need to quantify our theoretical errors when we make predictions, because there are observables with which to compare. And agreement between theory and experiment requires the errors on both sides to be small. And part of the theoretical error is the quantum error. And so effective field theories are playing an important role, starting to play an important role in cosmology. So the way I like to, this whole story is something which could have been lectures that could have been given, 30 years ago or 40 years ago, I guess now. It goes back to, let me make sure I can advance my slides here. It goes back to.
Excuse me, are you changing the slide or not?
I'm trying to, but I'm seeing that it's not happening. So let me just see if I can find the magic button here.
Yeah, at the moment
Here we go.
Oh, okay, great, thank you.
Yeah. Okay, good. Thank you for flagging that. If there's a problem like that, please do let me know if it's not looking like I think it should do. So these lectures could have been given when I was a graduate student, which was a long time ago. And these ideas are mostly the work of people who've been filling in the details of a picture that Steven Weinberg identified starting in the 60s, but he really articulated it very clearly in the 70s. You all know of him, of course, as the Nobel laureate who won his prize for the development of the Standard Model, one of the three, who won the Nobel Prize in '79. But I think in many ways, unlike many Nobel laureates, that may not be his best paper. This one is the one I'm going to be talking about. He wrote this paper in 1979 as well. And this is the paper where he lays out the program that whose fulfillment is what I'm describing. And the fulfillment has been the work of many people, but the vision for it was laid out very early. And here, I think this paper he wrote in '79 is something which he'd been saying this for a decade before that, and so it really is kind of a visionary work in the sense that the Standard Model is, of course, spectacular work, but this effective field theory story of Weinberg's really changes what we think we're doing when we write down a theory like the Standard Model. So it's really, if you have not read that paper, you should really read it. It's one of the classics. Okay, so the way I'd like to tell my story is in three parts. I'm going to first do I expect that most people have seen effective field theories, but I'd like to actually go through the background of effective field theories, because when we come to cosmology, there's going to be features of effective field theories that will seem unusual. For example, we'll be dealing with time-dependent backgrounds. And one of my messages is to try to not think of gravity. I'm against gravitational exceptionalism. I like to point out that many of the issues that you hit in cosmology when you're trying to think about it in this effective field theory way are issues that you also see in other areas of physics. And the way to deal with things is the same way as in other areas of physics. That's something which is often resisted in the gravity community, but I think effective field theories help you see things that way. So the first part will be a review of effective field theories if you've seen it already, but trying to highlight some of the things that will be relevant for cosmology later on. The second part is a review of cosmology. And so I think most of you have seen cosmology, but I'd like to put us all on the same page as to what we know and the things I'd like to use when it comes down to the last part. And the last part will be the specifics of some of the specifics of the many applications of effective field theories in cosmology. And you'll see that if you're in the business of modifying any of the rules in gravity, because you're in a regime where quantum effects are claimed to have been seen, you're in this unusual situation where it's not sufficient to think about the classical approximation in gravity and cosmology. And one of the questions that is part of that is what justifies the classical approximation in gravity, which you'll see is completely an effective field theory argument. There are many models in cosmology that don't make a lot of sense because they're not trying to quantify what controls the approximations, and in particular the classical approximation, which everybody makes. And part of this last story will be fixing that, identifying what the variables are that are important, and you'll see that it's a very standard. Given the first part of the lectures, it'll be a standard application of the first part in the last part. So those three pieces will divide up. So the mostly today we'll be talking about the various aspects of effective field theories, which are these. I'm going to be drawing from the book I recently wrote on effective field theories. The first 6 chapters of which are the ones that are the important ones, and those are available online. And I believe you have a link to them in the lecture note material on the webpage for the school. The cosmology part, I'm going to talk about I'll remind you of the basic story of expanding universe, but then the structure formation will be an important part of the story because that's part of my motivation, that quantum fluctuations and why they are a good description of structure formation. And the primordial fluctuations is the quantum part of it. So it's the cartoon of the picture as to the origin of the primordial fluctuations that we think are responsible, seeding the formation of galaxies. And then when it comes times to combine the two previous threads, I'll first remind you of how general relativity works as an effective field theory. And then we'll power count, and there'll be some various specific cosmology related topics we'll get to at the very end. And, if it happens that we don't get all the way through this, the slides will be available. I'll make the slides available. I haven't done it yet because I'm not sure how far we're going to get in each lecture, but the slides will be available. And it doesn't really, if we have to pick and choose amongst these topics, it's not a disaster. Oh, and I should turn my it's 8:28, so let me turn the timer on here. I want to make sure I don't run out of question time. So, all right, so let's dive in. So unless there's questions about the framework, my proposal would be to dive in right now. So let's start with effective field theories. And the basic idea here, I'm sure you all know, but I'll remind you. And it's basically, there's this fact of nature that it comes to us with many scales, and we don't need to understand them all at once. And that's why science works. So you didn't need to understand nuclear physics to understand atomic physics. Systems come with hierarchies of scale here. I'm thinking of hierarchies of energy levels. So if you think of an atom, the large splitting is coming from the spacing of nuclear levels. But for any one nuclear level, you've got the atomic levels, and those are much, much smaller. And that hierarchy between small energies or high energies and small energies, or large distances and small distances, is an organizing feature of nature. And the fact is the fact, which is the decoupling fact, is that in nature, most of the details of small distances, but not all of them, are basically irrelevant for understanding longer distances. And so in this atomic example, when I say most of them are irrelevant, you didn't need to know nuclear physics to understand atomic physics, but you did need to know the mass of the nucleus and the charge of the nucleus. So there's some specific things in short distance physics to which long distance physics is sensitive. Now, the great success of quantum mechanics and quantum field theory is that it has the same decoupling property as nature does. So that's a good thing. And on the theoretical side, it's kind of a trivial observation what's going on with decoupling. It's if you have some dimensionless observable here. Let me see if you can see my mouse here. I guess you cannot. All right, so let me see if I want to show you something. I guess you can see if I draw, but you can't see my mouse just generically, I guess, right? I guess that's right. That's okay. So the theoretical observation, if you have a hierarchy of decoupling, is that if you have a hierarchy of scales, let's imagine you have some observable here. Since you can't see my mouse, what I'll just do is I'll describe it. But if it becomes let's try this. Sorry. There you go. So now you can see something, I think, right? All right. So if we're looking here at some observable, some dimensionless observable A, it depends on a bunch of dimensionless parameters. I'm calling them collectively theta, but I'm imagining that there are two scales involved, energy scales, capital M and little m, which could be the nuclear physics scale and the atomic physics scale, if you like. The theoretical observation that things simplify when these are very different scales is kind of a trivial one. On dimensional grounds, you know that this can only depend on the ratio of these scales. And then if that ratio is small, the observation is that, sorry, let me turn that off, is that the Taylor expansion is a good approximation, and there might be logarithms involved, but as far as powers are concerned, Taylor expansion is a good approximation. And of course, the expression for the observable in the limit that the small parameter is 0 is particularly simple. And the only thing that really is going on with effective field theories is that the fact that things simplify is really just the expression, the statement that functions simplify when you Taylor expand them in small arguments. But the effective field theory technology is saying that you really want to do that as soon as possible in a calculation, because you want to simplify things as soon as possible. And the observation is also that you can do the simplification for all observables at once if you do it in the Lagrangian rather than doing it observable by observable. And so it makes it very efficient way to approach situations with hierarchies of scale. Now you might say, maybe you're not interested in things with hierarchies of scale. Maybe you're doing cosmology and there isn't, and you're interested in one particular scale. The real utility of these ideas is that you have no options about whether or not you're dealing with hierarchies of scale, because quantum mechanics is always forcing you, if you do things accurately, it's forcing you to involve high energy scales, even if you didn't think you were. So classic example is this expression here for the energy shift of a particular energy level. And once you get to second order, it has this famous sum, and that sum includes all possible energies arbitrarily high, and they're not suppressed by much. Although the terms where the energies are large are suppressed by a denominator, there's only one power of energy in the denominator. That's really not enough to make it irrelevant. And so the whole story of decoupling of scales is really important in quantifying errors. Even if you nominally think you don't have a hierarchy going on in the scales of interest to you, there are scales that you're not paying attention to, for which these hierarchical arguments can matter. All right, enough said. So that's the qualitative thing. What I'm going to do is I'm going to work through a simple example just to illustrate the features that I want you to keep track of when we get into the cosmology part later on. So I'm going to take this vanilla example, which I think everybody's familiar with. And if you're not, if you weren't familiar before, you will be once we're done. I'm going to take this, so we'll have a theory of two scalar fields, one's complex scalar field or two real scalar fields, interacting through this Mexican hat kind of a potential, which is minimized at non-zero values for the field. And this has kind of all the ingredients that you need to explore effective field theory methods. We'll treat it perturbatively. So we're going to imagine that the coupling lambda is small. So if I turn this laser pointer on again, we're going to imagine that this coupling lambda here is small. And so then we'll expand around phi equals v, which is the minimum of this potential. And R and I are the quantum fields that will be interested in the interactions of. All right. So what we do in perturbation theory is we take that action and we write it out in terms of R and I, and we just do the expansion that I'm indicating here. And when you do that, there's a piece which is quadratic. this thing has been designed so that when if we take the action evaluated at v, it's 0. The derivatives are 0, and the potential has been designed to vanish at 0. There's no linear piece in the expansions because v, phi equals v satisfies the equations of motion, and the linear piece would have been proportional to the equation of motion. So the first thing you see when you expand everything out is something quadratic, and that's what we're going to call that's the thing we'll perturb around. That's our free action, and then we have the interaction terms, which are the cubic and higher terms. In this case, there's only cubic and quartic terms, and you see here what it is that you get when you do that. So now the standard story is the quadratic part is telling us the spectrum, the free spectrum, it's a bunch of harmonic oscillators. In this case, each momentum mode is a harmonic oscillator. We have a dispersion relation where the energy squared is a momentum squared plus the mass squared, and the masses we can read off from the non-derivative terms of the action. In this case, the only thing involving the fields undifferentiated in the free Hamiltonian or the free action is the r squared term. So that shows you that the r field gets a mass, and the size of the mass is given by lambda v squared, and the mass squared is lambda v squared. And the I field is massless. You're not surprised to see. And the hierarchy we're going to be interested in for the effective field theory story here will be we'll be interested in energies much less than this mass. And so imagine we're in a world where this is what's going on. We're building the Large Hadron Collider to explore the physics of the I particles, and maybe we knew about the r particles, maybe we didn't. And we want to know what the cross sections are of scattering of these various particles with one another, and we'll compute them perturbatively in powers of lambda. Our Feynman rules are going to be built from these interactions. So there's two kinds of cubic ones. There's an r cubed thing. I'm using solid lines here to describe the heavy field and dashed lines to describe the light field. And there's an ri squared term, which is a cubic interaction with two lights and a heavy. And you see from the action that they come with a Feynman rule proportional to lambda v, both of those interactions. And then there's a quartic interaction. There's several quartic interactions. There's 4 heavies, 4 lights, 2 heavies, and 2 lights, all of whom have a coupling which is proportional to lambda. And so off we go. We can calculate scattering. And so you might have thought what we should be doing is, if we're perturbing in powers of lambda, is keeping in the graphs that I've drawn here, keeping only the first one, which has 1 power of lambda, whereas the second one looks like it has 2 powers of lambda. But of course, one of the things that's going to emerge is that what organizes the lambda expansion is actually loops rather than explicit powers of or numbers of interactions. And so we'll see that the higher powers of lambda actually corresponds to higher loops. And with that in mind, these are the tree graphs that would be involved in the scattering of 2 light particles with 2 light particles. We evaluate that using those Feynman rules. Then the first graph gives you that first term there, which is just proportional to lambda. This is, I'm giving you here the invariant amplitude for the scattering. And then in the same normalization as the first term, the second graph plus the cross graphs where we interchange the external lines for the initial and final states gives you the 3 terms in the square brackets where the various terms are coming from crossing. You can see that the factors of lambda and lambda v that are required by the Feynman rules are what they are, and then there's kinematic dependence on the masses as well. And you can also see why these are competing in size, although nominally the second graph looks like it's order lambda squared. It also involves m squared, and m squared itself is proportional to lambda v squared. So you see that the m squareds in the denominators of the second graph carry a lambda, which is canceling one of the lambdas from the vertices. And so these are really graphs that are both the same size and powers of lambda, if we hold v fixed, the parameters in Lagrangian. Now, for the purposes of low energies, we can ask, what's this look like at small energies? And if we Taylor expand it out, you might have thought it's going to look like lambda, but it's not. It actually vanishes. The first few terms in the expansion in powers of energy over m vanish. It turns out you have to go out to 1 over m to the 4th order before you see something non-zero. And this is the leading contribution that you get. So that's kind of weaker than you might have expected, right? In the low energy limit, it's not something which is just order lambda. And if you were in a world like this and you were building your Large Hadron Collider to explore the properties of the high energy theory, this would be a worry for you because all the scattering is going to be smaller than you thought. And you'd really want to know, is this an accident, right? You'd want to know maybe it's true that this leading piece goes like energy to the 4th over m to the 4th times lambda. But if I worked to higher order lambda, maybe that's no longer true. Maybe maybe it's actually worth going to higher orders in lambda, because even though lambda is small, it might be that lambda, the suppression by powers of lambda might not be as small as suppression by powers of E over M. And so it might be worthwhile working the second order in lambda. And of course, if you did that, you just find that it's still true that if you work to higher order in lambda, this amplitude is still proportional to 1 over m to the fourth. And if you did this order by order in powers of lambda, you'd find that to all orders in powers of lambda, this amplitude is suppressed by powers of energy over m. And the hard way to learn that is to do all the calculations order by order in lambda and see that it's always true that the scattering at low energies is smaller than you thought. Effective field theories are going to be what organize the way to think about this, and they're going to identify very efficiently what the suppressions are in everything in powers of energy over m. If you had access to the heavy particle R and you did the same calculation for R light heavy scattering, there's a similar thing that happens. The Taylor expansion for small energies no longer starts at 1 over m to the fourth, it starts at 1 over m squared in this case, but it's still true that it's suppressed, and it's also true that that suppression holds to all orders in lambda. So, as you know, that's not an accident why that suppression is happening, because the light field is light because it's a Goldstone boson for symmetry. And there's a theorem, Goldstone's theorem, which is saying that in the low energy limit, those particles decouple. Is there a question there? I kind of heard something. Feel free to break in. But breaking in also helps me assess the level. It's very difficult to give these lectures online. The only thing worse than giving lectures online is hearing lectures online. So I kind of feel for you guys, but it's very difficult to, what you can't do online that you can do in the room is sense whether the room is with you or not. And there's two ways in which the room might not be with you. It might be too elementary a presentation, or it might be too complicated. And the questions really help pin that down. So please do ask questions.
Okay, then can I ask one question? So
please
you can also define the fields as like R times e to the I, e to the I kind of.
Yeah.
In the case we don't have the 4-point vertex of I, right?
Yeah, I'm about to do that actually.
Sorry.
I'm about to do that, but go ahead, ask your question, and I'll answer it if I'm not. I may answer your question in the next few slides, but please ask it anyway.
In that case, I mean, there is no kind of cancellation or some. I mean, it's in that case the leading order is just a.
It's much more obvious what's going on in those variables that you're describing. That's true. Yes.
I'm confusing that the scattering amplitude don't depends on the field definition, right? So, I mean,
yes.
Wondering the structure how to change in that case.
Well, so let me press on for like 2 or 3 more slides, and then I'll check it and see if you can re-ask the question if I don't answer it, because I think what you're asking is actually, I think you're asking the key question, and it's that's actually the message of these next few slides, and that is that part of the problem in the way I'm presenting it, you're rightly saying, is that I'm using stupid variables. In the end of the day, I'm using the R and I fields, and there's a better way to express. There's a better set of fields for which this suppression at low energies is more obvious. So then the question is so how do you find what the best fields are? What's the rule for making making things as obvious as possible, which is what you're trying to do when you make these calculations efficient. And that's kind of the message of these next few slides. So setting that up, I want to remind you that the reason that this light field has the special properties is there's a symmetry reason for it, and that's because this whole problem has this rephasing symmetry that this complex field phi gets when you multiply it by some phase. That's the symmetry of the action, and the idea is that the idea behind the change of variables that you mentioned is let me show the slide. If I were to, instead of using R and I, if I were to use polar coordinates, so I write phi as being a modulus times a phase. So xi is the phase and chi is the modulus. And I'm again expanding around the field equals V. These are the variables I think that you had in mind. They have the property that what's nice about these variables as opposed to the old variables is that under the symmetry where you rephase phi, in the old variables, the fields R and I rotate into one another in a way that I'll make explicit in a second. But in these new variables, what happens is that xi changes and chi doesn't. And xi changes by a shift because we've made xi the phase of the field. And so you can kind of see that if I take xi and make it constant, so I go to the long wavelength limit where xi varies very slowly as a function of position, then nothing will depend on xi, just because in the limit that xi becomes a constant, that constant is just the symmetry. I'm free to shift xi by a constant, and that's nothing changes when I do that. The action doesn't change. That's what it means to be a symmetry. So if xi becomes constant, it'll have to drop out of the action because of the symmetry. And that's kind of what's going on. That's why the light field scattering, xi is going to describe the light field, and it's going to be basically dropping out of everything, including the mass term. And that's why Goldstone's theorem works, is that it's whenever you have a symmetry that's broken by the vacuum, there's a particle that wants to drop out of the problem at low energies because it's parameterizing the symmetry direction. So if we just take this change of variables and just repeat the exercise, so just take the same action and write it out in powers of xi and powers of chi, you get a slightly different, it's the same logic, but the answer is a little bit different. So we have again a quadratic piece, and we have again interaction pieces. But the main difference about these interaction pieces is that with the light field, xi is always appearing differentiated. So everywhere and that's really a reflection of the symmetry. The whole problem had the symmetry where xi shifts by a constant, and because of that, the action could only depend on xi through derivatives, because that's the way it becomes invariant under this shift. And so that derivative structure of the interactions makes the Feynman rules much more transparent into what's going on at low energies, because any interactions involving xi are necessarily going to involve derivatives, and those are powers of momentum. So that makes the suppression of the scattering at low energies much more obvious, because if we do the same graphs, these are again the ones that are going to dominate, but now we're using the Feynman rules for this Lagrangian. You see, as you pointed out, that there's no longer a direct contact interaction, but you do have the thing the exchange graph is involved, but it involves explicit derivatives at both ends. And so the fact that you've got 4 powers of energy in your amplitude is obvious for these variables. And if you kind of go through the exercise of calculating the amplitude, you get exactly the same formula I gave you before. But it comes to you in a way where it's much more obvious that the low energy limit had to be suppressed by powers of momentum. You get the same answer because field redefinitions don't change anything physical. And scattering amplitudes are physical, so you can measure them, and so they can't change. And so this is a special case of this general observation. You'll see that Weinberg is sprinkled throughout these ideas, because many of these things go back to him. And he has these 3 laws of theoretical physics that he put down in one of his review articles. It's the article called "Why Renormalization is a Good Thing." But one of his 3 laws is that you can use any variables you like in a physical problem, because nature doesn't care how you label your variables. But if you use the wrong ones, you'll be sorry. And in this case, the scattering amplitude doesn't care which variables you use, but if you use the R and I variables, then you work harder, because the suppression of the amplitudes isn't obvious at low energies. It looks like a miraculous cancellation. Whereas if you make the symmetries explicit by using the xi and chi variables, then the low energy properties of the amplitude are obvious from the get-go. And the reason that was simpler was, and the reason that's important for effective field theories, is that in this particular theory, we have a heavy field R and a light field I, and the original way we were thinking about the symmetry involved them mixing into one another, so that there was a rotation which took R to I. But if we now focus at low energies and we imagine integrating out the heavy field R, it's not useful to have a symmetry which is relating a field I no longer have to a field that I do have. So this linear realization of the symmetry is no longer useful if the 2 things involved in the symmetry have such different masses that I can integrate one out and not look at it and focus at low energies only on the light masses. It's much more useful to phrase this, to choose variables such that the symmetry is manifested on the low energy degrees of freedom alone, because then the consequences of the symmetry will be more clear. And in this case, the variables that do that are chi and xi variables. That's how you would have found them. You see, you're trying to identify the fields that are at low energies that are carrying the information of the symmetry. And in that case, this is what's normally called a nonlinear realization. In this particular example, it's linear. It's an affine transformation. It has a homogeneous shift, so it's not strictly linear. But in general, the kind of low energy transformation you could have had if we'd had in a non-abelian symmetry would have involved a non-linear function of the fields. The transformation rule itself wouldn't have to be linear in the fields. But there usually exists a way of phrasing the symmetry which acts only on the low energy degrees of freedom, and that's usually the useful set of variables to use. So I don't know if you want to re-ask your question if I covered what you wanted to say.
No, it's fine.
Okay, because that's the one of the key issues in effective field theories is identifying the efficient degrees of freedom, and one of the organizing principles for that is to identify those variables for which symmetries are acting in a way which map low energy states to low energy states. And in this particular case, that's what's nice about those degrees of freedom. You know, there are some things when you do changes of variables that will change. If you look at a correlation function of the fields, that'll change. Or if you ask, is this theory, does it look like it's renormalizable or not? You can make a theory look like it's not renormalizable. You can make a renormalizable theory look like it's not renormalizable by doing a nonlinear field redefinition. But the physical things, in this case, the scattering amplitudes, don't care. And that's always true. It doesn't matter what variables you use. If you're careful, the physical things won't care how you parameterized what you did. Intermediate steps might care, and that might be important in making the calculation easy or not. But in the end of the day, physics doesn't care. Okay. All right, now the effective field theory message is that this low energy amplitude, which this is you calculate this using either of the sets of variables. It's easiest to do in the second set of variables. It always has the property that it's dominated by the 1 over m to the 4th term. And of course, the effective field theory observation is that if we had just taken at low energies our theory to be a free I field interacting through this particular interaction that I've written here, that would have captured the 1 over m to the 4th piece of the effect of the scattering amplitudes perfectly. If I just take that Feynman rule for this particular Lagrangian with this particular coefficient, lambda over 4m to the 4th, that gets it right. But what's more remarkable is that that's not just true for this one scattering amplitude. It's actually true for all observables. If you work to order 1 over m to the 4th for every single observable in this theory, they all are captured if you use only the light degrees of freedom by this particular effective interaction. And if you wanted to work to order 1 over m to the 6th, you could complicate the effective action a little bit by adding a 1 over m to the 6th term to it. And it would still be true that every single observable gets captured. The low energy limit of it is captured by this effective Lagrangian, by some sort of an effective Lagrangian. And that's the magic of effective field theories, that if you're only interested in low energies, and if you can't see this R field, you're really only interested in this Lagrangian. It's a very efficient way of organizing the low energy information in your theory, because it does it explicitly only in terms of the light fields of your problem, the ones that are in the low energy theory. And the modern picture is that every single field theory we have has this character. It's one of these low energy effective theories. So you might ask, so why did that work? It seems like a miracle that you can get all the observables that way. And there's several deep reasons underneath it. One of them is it kind of had to work in the sense that what we've really done is we've taken the full theory and we've projected it onto some low energy limit if we've decided to look at energies below the mass of the heavy particle. And at some level, what we've done there is we've projected onto a set of states that are defined by energy. So we're looking at states that are below a given energy. So that will commute with the Hamiltonian. And so that projection will commute with the time evolution. So there had to exist some sort of we knew that the full theory involving the heavy and light fields has some unitary evolution involving the whole Hamiltonian. So there has to exist some Hamiltonian involving only the effective fields, only the light fields that will capture the same evolution, because energy conservation is basically making everything work. Because we're using a conserved thing, energy, to project out heavy states. If we start only with low energy states, energy conservation will keep us from ever getting high energy states. So there, and because the low energy fields, the field I is a complete set of, the creation and annihilation operators for that is a complete set of fields for any low energy degrees of freedom. There has to exist some Hamiltonian involving the light field that will capture all the physics at low energies. That's kind of a guaranteed for us because we're projecting onto a subset of the Hilbert space defined by a conservation law, and in particular energy conservation. So this is another one of Weinberg's pieces of wisdom, is that basically quantum field theory doesn't have a lot of content to it. It's just basically encoding basic motherhood issues like invariance under special relativity, unitarity, cluster decomposition, which is the statement that amplitudes factorize if you separate them in the spacelight direction. So probabilities of scattering on Mars factorize from probabilities of scattering on Earth at the same times because those are statistically independent, so the probabilities should factorize. So the very basic things are being encoded in quantum field theory. That cluster decomposition in particular is what's driving the locality of quantum field theory. And the fact that we have a quantum field theory that's describing the low energy limit of our theory isn't a miracle because there's really not a lot of content in quantum field theories beyond just these motherhood issues of quantum mechanics. But that doesn't answer why the answer was so simple. You know, we had an integral over a local thing. It was just a bunch of derivatives of the fields, polynomials at a given point. The particular example I showed, we had a 1 over m to the 4th term. We didn't have a 1 over m squared term. Why didn't we have that? So those are also, there's simple answers for. The locality is a deep thing. It's always true that these effective actions are local. And it's because of basically the uncertainty principle that, you know, we're at low energies. If we scatter light particles with one another, there may be a virtual heavy particle that gets exchanged. But we're never producing it as a final state because energy conservation forbids it from being produced if we're at low energies, if we start off at low energies. So that means that these heavy particles can only contribute as virtual particles. And then the reason that's true is energy conservation. But the reason they can appear virtually is that you could think, one way to think about it is that the uncertainty principle allows you to violate energy conservation, but provided you do it fast enough. You can't do it for long times, but you can do it for times that are above the order of the 1 over the energy conservation failure you're doing. So in this case, because the energy you'd need to produce heavy state is of the order of m, what will happen is that if you look any effects of a virtual particle of mass m at low energies will have to only have an influence over times that are of order 1 over m because of the uncertainty principle. And that makes them local effectively in time. If you can't resolve times that are as small as 1 over m, then anything that's happening in a time interval 1 over m is going to look to you like it's local. And that's what's going on. So because we've projected to low energies, things will be local in time. In relativistic systems, if it's low energy, it's also small momentum. And so that will also make things local in space. In non-relativistic systems, that's not necessarily true. You can have low energies and not small momenta. And so it needn't be true in non-relativistic theories that local in time is local in space, but in relativistic theories it is. The way you'd see that mathematically is if you look at these propagators that are describing these virtual particles and you Taylor expand them in powers of 1 over m, then you see that the e to the I px, when you integrate it, is giving you a delta function, and the powers of p over m times that are just giving you derivatives of delta functions. So as soon as you work to some finite order in 1 over m, you're always looking at different derivatives of the delta function. So at any finite separation, they're always vanishing. So that's why things are always looking like they're local. Now, there were things that you could have imagined writing down.
Sorry,
yeah, go ahead. Question.
I have another question. So now, in this sense, locality is only a property of the effective field theory, right? So
yeah.
In that sense, locality is not a kind of property of ultimate theory we want.
It need not be, as far as this is the way I'm arguing it, that's true.
Okay.
So I think that, and so there's a deep question there, right? So now if you're making up, what's going on at high energies, should you be requiring yourself to be local? Right. And I think that's always a hard question to ask. And what I always do whenever that question comes up is think about string theory, because string theory is a concrete example of a theory which does seem to make sense at high energies. And you can ask all these questions very precisely there. And there's a sense in which it's not local, in the sense that in string theory, particles are replaced by strings. And so that's the length of the string that is setting a fundamental scale. And so there's a sense in which it's not local, but there's also a sense in which it's local, because one thing that locality often means at low energies is analyticity of the S matrix. And in string theory, the S matrix still is analytic. And I think it's probably not completely understood exactly what version of locality is going into analyticity of the S matrix. So I think that there's part of your question is a good one, that there may be some criterion at high energies that if we could put our finger on it, it would restrict the options. And string theory is probably a working example of something which is not quite local exactly, but is almost local in the sense of the S matrix is analytic. One of the clues is that we do know at low energies, this cluster decomposition property, we do know that the probabilities had to factorize if they were space-like separated. That's kind of built into our field theories from the get-go. And that's part of why this is also local. And if you violate that, then some things that we believe are true would start to fail. So the possibility of spontaneously breaking symmetries, where you have a vacuum which is breaking a symmetry because the field has chosen a value which is not invariant in the symmetry. That's possible because of this cluster decomposition story, it turns out. And so there are probably experimental constraints onto how badly you can violate locality at low energies. But I don't think anyone's ever actually sat down and worked them out very carefully. So it's a very deep question. And I'm going to basically just take the point of view that at low energies, things are local because we built in cluster decomposition into field theory. And that's kind of an accident of the low energy limit. And I'm not going to commit myself to what's going on at higher energies.
Okay, thank you.
Good question. Okay, so things are local. But what this doesn't, so another question was not generic about our example of the effective theory was that it went like 1/m⁴. You know, and there are interactions we could have imagined writing down, which would go like 1/m². What happened to them? Why didn't we need them? So here's some examples. You know, the first line of this Lagrangian is what we've been talking about. That there's a free part for the low energy field Xi. There's the λ/m⁴ interaction term. But I could have written, you know, there's also I've written down something there that goes like 1/m⁸. That is there. You can calculate what its coefficient is. But if you're doing a 1/m expansion, one of the questions is, why wasn't there a 1/m² term? That should have been bigger, right? So I guess actually I may be getting ahead of myself here. Let me before I say that, let me first say, so given that we're looking for local Lagrangians, that there should exist a local Lagrangian that captures everything at low energies compared to m. You know, here's a bunch of local things involving more and more fields. And on dimensional grounds, you see that the more fields and the more derivatives I have, the more powers of m I need to make the dimensions work. The Lagrangian has dimensions of mass to the 4th in fundamental units. The action has dimensions of h bar, so it's dimensionless. And there's an integral d4x, so that Lagrangian had to have dimensions of mass to the 4th to cancel the d4x. And so all of these terms, so the first term here, a derivative is 1/length, so that's got dimensions of mass. So the fields have to have dimensions of mass to make this first term have dimensions of mass to the 4th. That's what it means to be canonically normalized. That's kind of why this coefficient is dimensionless. But once you've done that, everybody else has coefficients of m, which are given by dimensional analysis. And you can just kind of see here, we've got dimensions of mass to the 8th here. So we needed m to the 4th on dimensional grounds. In this term, you need m to the 8th on dimensional grounds because we've got mass to the 12th, I guess, here. That kind of shows you that because the fields have positive dimensions of mass and the derivatives have positive dimensions of mass, almost anything you write down, given that it has to be local, is going to be some polynomial of fields of derivatives, and they all cost you dimensions of mass. You're always going to have masses in the denominator to compensate for that. You're not going to get interactions where I get huge powers of mass in the coefficient just on dimensional grounds. And so what's nice about this local Lagrangian is that there's not going to be the number of interactions that are necessary at low energies is never going to be very complicated, because every time I make something more complicated, I need to pay the power of more powers of 1/m. That carries within it an observation which is true, that the interactions that should be the most important in nature are the ones that don't involve 1/m at all. That class of interactions is what we mean by renormalizable interactions. And it's true that renormalizable interactions play a special role in physics. Quantum electrodynamics famously is renormalizable. And the reason why it's renormalizable is this, that it becomes important to the extent that anything heavier that you're not interested in is so heavy that 1 over m effects are irrelevant. And then whenever that's true, you will be dominated by the piece which has got that's not suppressed by powers of 1 over m. In this particular example we have here, the only thing I could write down which involves positive or no powers of m would be polynomials in C. As soon as I differentiate it and I take 2 of them, then I always have things going like 1 over m. But these particular terms, which could have been in a normalizable theory, are being forbidden by the symmetry where C shifts. That's why we didn't have them. But if they were there, they would be the most important thing. So now let me go back to the 1 over m squared story. So why didn't we write down these interactions? They have fewer suppressions by powers of 1 over m. They should have been the most important ones. And the reason they're not there is important. So the important thing here is that both these interactions, if you wrote them and you calculated anything physical, they wouldn't contribute to it. So if you'd done the scattering with these interactions, you would have seen that nothing depends on A1 and A2. And that's because these interactions are redundant. And so it's important to know when interactions are redundant, because then they're not relevant to whatever you're trying to calculate. You waste your time keeping them. So there's 2 reasons why these ones are redundant. If I take the right-hand one and I integrate it by parts, I can write things that way, where the second term now in the box there is a total derivative. And because of the total derivative, the integration by parts has moved part of the second term into the first term. So I've changed the coefficient of the first term. Now, total derivative is something which doesn't contribute. The Feynman rule for a total derivative is proportional to the sum of the momenta in that vertex, and the delta function of momentum conservation makes that 0. So in a total derivative doesn't appear in Feynman rules because of momentum conservation. Another way to think about that is in the path integral, it's a total derivative. It only really sees the boundary. So if you don't ask a question about the boundary, then it doesn't matter. It doesn't depend on the fields in the interior of the path integral. So things that are total derivatives are redundant. You can drop them unless you ask a question that cares about boundaries, or an instanton-like question that cares effectively about boundaries, or cares about the large spatial boundary, which is at infinity. Second way, that's why one of these terms wasn't important. But you might have asked, why doesn't the first term contribute? It's not a total derivative. And the reason there is that term can be removed with a field redefinition. And again, changing variables doesn't change any physics. So if I can remove this thing with a field redefinition, then it can't appear in anything physical. If you did calculate the scattering rate, you'd see that this thing is proportional to 0, because it would be proportional to box of the external line, and the momentum squared it'd be proportional to the energy squared plus the momentum squared, or minus the momentum squared minus the mass squared. So it would vanish because the particles are on shells. So the dispersion relation of the particle would make it 0 if we had kept it. So the field redefinition that you would need to get rid of this term would be this one. If you shift the field by a derivative of the field, and you do it perturbatively in 1 over m, then the kinetic term, the leading piece, goes to itself plus a correction, which is exactly the opposite sign of the one that we had, and so we would cancel it. And it would introduce things in order 1 over m to the 4th, but you could order by order do this. Anything that you can get rid of by, because it's coming as a change of the lowest order action, the rule is that anything in your Lagrangian your interaction Lagrangian that vanishes when you use the equations of motion of the 0th order term. In this case, box C equals 0 is the equation of motion from the 0th order term. Anything that has that form can always be removed by varying the fields a little bit, because the variation of the first term always is proportional to the equation of motion. And so that's the reason why the first term there is also redundant. All right, long story short, we can always find an effective Lagrangian. And now, how do you construct it? So let's just, this is something which I think is more familiar, so I'll just kind of go through this quickly. So the way you formalize this is, you imagine you have light fields and heavy fields, you're doing a path integral over both of them. The assumption is that we're only measuring the properties of the light field, so we only look at observables that involve the light field L. Then the idea is we like to take advantage of this expansion in powers of little m over big M as early in the day as possible. And here I want to make the case that you can do it in a way which applies to all possible observables at once. So the observation is just do the integrals in steps. So to do the integral over h first, the observable by assumption doesn't depend on it. So if we integrate over only the heavy fields, we could define the answer of that integral to be e to the I s lambda, what I'm calling s lambda. That's the definition of what it means, what that integral gives you. And if I had done that, then the remaining integral over the light field has the form the same form as the original thing did, where the action for the light field is S lambda rather than S of L lambda of the light field and the heavy field. So that shows you that if you do the integral over the heavy field, i.e. integrate it out, then you can define an action, what we call the Wilson action. And then the way that you could compute any observable involving light fields is you treat the path integral the way you would have done anyway, and you just treat this effective action, this S lambda, as if it was the classical action, and then you're done. It's important that everything here depends in detail on how you split the heavy and light fields up. So I've written things, the integrals on lambda, as if they depend on lambda, but they depend on all kinds of details about how you did the split, how you decide what's heavy and what's light. But the important thing is that although S lambda will depend on lambda because that's the lower limit of the H integral, we are guaranteed that once you put it into the integral at the bottom of the slide there to get the observable, that the lambda dependence cancels because it wasn't really in the answer. In the top line of the slide, there was no lambda. And all that's happened, lambda is only appearing because we're doing the integral in stages. And so if you imagine having two graduate students, the first one does the integral over the heavy fields and then stops and they take a break for the day. And somebody walks in halfway through and looks at the remaining integral, they'd say, oh, you're just doing an integral over some classical Lagrangian S lambda. And they could do that integral themselves. But the one thing that would not be a miracle is that lambda is not in the answer because lambda wasn't in the original answer. Lambda is only a bookkeeping thing, and it's telling us how we're doing the order in which we do these integrals. So that's important. So, so the lessons are, if we knew what this S lambda was, we have all the information of the heavy fields once and for all. And so if we do the series in 1 over m in particular in that action, we can apply it to any observable in the problem once and for all, because those observables didn't care about the heavy fields. And that's kind of why it's useful to do the Taylor expansion in the action rather than for each observable separately. Once you know the effective action from one observable, you know it for all observables. And this cancellation of the details of S lambda depend on lambda and all the details of how you split heavy from light. But those details drop out of physical things is the important thing. And of course, that smells like renormalization. If I told you that you have an integral where you're doing an integral over some light fields and it depends on some cutoff at the top end of what your light fields were, and then I told you that doesn't matter what that cutoff dependence is because all your couplings in your Lagrangian, in your action, also depend on that cutoff in just exactly the way they have to cancel. That's the way you classically phrase the renormalization program, that any divergences you get in some loop integral can be absorbed into couplings in your problem. This is why it works. It always sounds like a miracle when someone first tells you that you can absorb divergences into coupling constants, but it's kind of mundane in this way of phrasing it. We knew that the answer, the way we derived the action in the first place was by integrating out heavy things, and that's why it depended on all these lambdas. And so the understanding of why renormalization works is kind of mundane in this effective theory picture. And that suggests that in the classical effective theory, in a classic renormalization program, where you have a classical action and then you quantize it and then you absorb divergences into the parameters, what you're really, it doesn't make sense to think of it as being a classical action. What it really is it's just another one of these Wilson actions, this S lambdas coming from some higher energy degrees of freedom that you didn't know what they were, but they were there. And so the cancellation of divergences that people talk about normally is just really this removal of scales. What you really have is a series of Wilson actions that are describing physics at different scales. And you don't have a classical action and a quantum action. It's just they're all quantum, but they just apply to different scales. That's a very, very beautiful picture, which seems to work. Now there's a technical point, which is going to be important for gravity. And that is the way I'm phrasing it, it sounds like cutoffs are important in this whole problem. And it's much easier to use dimensional regularization. And the way I'm phrasing things, it sounds like you can't use dimensional regularization because dimensional regularization includes all possible scales. And I want to first convince you that that's not true. It's actually better to use you can define effective theories with a dimensional regularization, and you should if you can. So in this picture, on the left-hand side, what you should do is this is the cutoff picture. I'm imagining you've got these two scales, a heavy one and a heavy mass and a light mass. And what I've been describing so far is I've put in some scale lambda in between them And I've defined the heavy theory to be the high energy pieces of the light field and all the modes of the heavy field in the heavy theory, in the UV theory. And the low energy theory is just the low energy parts of the light field. In dimensional regularization, what we would do is we would actually just say, for energies above the heavy mass, we'll have a dimensionally regularized theory involving both fields, all possible modes of both fields. And in the low energy theory, we'd have a dimensionally regularized theory involving all possible modes of the light field. And at first sight, that sounds kind of weird, but it works because the difference between these two descriptions, it only really cares about what this slide is doing is it's saying what I just said, that the difference between those two descriptions is what we did with the high energy modes of the light field. In this case, they're in the high energy theory. In this case, they're in the low energy theory. But those are just special cases of high energy modes. And the whole point of effective field theories is that anything at high energies can be expressed in terms of a local interaction. So the difference between dimensional regularization and not dimensional regularization is a high energy effect. You can just change all your effective couplings in a way that will capture that difference. So there will exist effective couplings in the dimensional regularized case. And that's actually super useful because in dimensional regularization, if you're trying to estimate on dimensional grounds how things depend on energy, it's very hard to do in this traditional way of thinking about it, because the scale lambda is a big scale compared to the low energy scales. And so it makes dimensional analysis hard. But in dimensional regularization, you don't have those factors of lambda, because the change from the effective theory to the high energy theory happens at the heavy scale m, which is a physical mass. And so only physical scales are appearing in your answer. So what's useful about effective theories is that they allow you to quantify which interactions are important. So I kind of have been going through, like, I write down an interaction and you don't know in advance which ones are going to play a role at any given order in perturbation theory. Now we can be precise about exactly which interactions have to be included to any order in this small 1/m expansion. So let's imagine we have some effective Lagrangian, and I parameterize it in this way. I factor out some scale mu to the fourth, so that everything else is dimensionless. And I have a bunch of effective interactions, which I'm calling ON. N runs over all the interactions, and it involves d derivatives, and each interaction has d derivatives and f powers of the field. And I'm on dimensional grounds compensating for every derivative with a scale capital M, and every field with a scale V. So I've got three scales, mu, M, and V in principle, which I'm going to keep track of. The Feynman rules for each of these interactions will be something involving F external lines, because there's F fields, and they'll have D powers of momenta because of the D derivatives. Now we draw some graph. It's got L loops in it. It's got V vertices of each type, Vn vertices of type N. It's got E external lines. And what we do is we identify where the powers of mu, capital M, and V are just using the Feynman rules. It'll be coming from a dimensional grounds. And then we'll do there'll be some loop integrals we'll do, and those would have been complicated depending on cutoffs and everything if we had not been using dimensional regularization. But in dimensional regularization, the only scale in the low energy theory will be the physical external momenta, which I'm going to call Q. I'm going to assume that all those external momenta are the same size, basically. And then on dimensional grounds, I get to tell you what the power of the low energy scale is. And the dimensional regularization isn't changing the dimensional argument at all. All right, so now for this graph with E external lines and L loops, I can tell you what the dependence is on mu, M, and V. And that involves two facts. The first fact is we have to use two facts that come from the construction, the topology of a graph. So one thing is that and that's basically expressing that the internal lines, the number of external lines, the number of vertices is not independent of one another. And there's two reasons why they're not independent. The first one is what you call conservation of ends, that if I count the ends of a line, there's two ways of doing that. I could just count the things coming out of a vertex, or I can count 2 for every internal line and 1 for every external line, and those numbers have to agree with each other. So here's the way of counting ends of lines by counting the lines. Here's the way from counting the vertices. I have to sum over all the vertices, the number of vertices times the number of fields at that vertex. So those have to agree with each other. The second fact is basically the definition of what it means to be a loop. So if you had a graph that you could draw on a plane, this expression here is a topological identity. It says that anything you can draw on a plane it has the topology of a disk in 2 dimensions, and the Euler number of a disk is 1. And the Euler number of a graph is given by the number of faces minus the number of edges plus the number of vertices in a graph. And so if I wrote these 2 terms on the left-hand side, I would be saying the Euler number of the graph is 1, where L is the number of faces. That's the number of loops in my graph. But there are some graphs you can't draw on a plane, that they have lines that kind of cross each other in 3 dimensions, let's say. And so you can't draw them on a plane. So for those graphs, this is the definition of what L means. And so, so L is given by 1 plus I, number of internal lines minus the sum of the vertices. That's something which on a graph on a plane would agree with your naive notion of what a loop is, but this is what we're going to mean by loops in practice. All right, so now what we do is we just count all the powers of mu and m and v based on Feynman rules for each vertex. And then there's some integrals that we have to keep track of. And on dimensional grounds, we imagine keeping track of the integrals by using the dimensional analysis where we take some power of the external momentum given this Lagrangian. And that leads us to the following formula. So this amplitude has to depend on these scales in the following way. So it has an overall factor of mu to the 4th. There's a factor of 1 over v for each external line. There's a factor which counts the number of loops. And then there's a product of all the interactions of q over m to some specific power that depends on the number of derivatives and the number of vertices having those derivatives. So the first thing to observe here is that all the q's are in the numerator. And so the low energy expansion where q is small compared to m, mu, and v has a chance of being a good one. And that's essentially what's going to organize perturbation theory. In particular, the number of loops is being counted by q divided by this combination of scales here, qm divided by 4 pi mu squared. Second observation is that v only appears in this overall thing and not involving powers of q. And that's expressing the fact that at low energies, the derivative expansion is logically independent of the field expansion. It might be that in your theory, large fields does not mean high energies. And so in that case, you should be able to have as many fields as you like without worrying about violating the low energy limit. And this is just the rules of the Feynman graphs expressing that. So there's nothing that you should really think of the field expansion and the derivative expansion as logically independent. And in this case, 1 over v is counting the field over v is counting the field expansion. Derivative over m is counting the derivative expansion. We're going to use this formula for gravity in great detail. So this formula for gravity explicitly says gives you the circumstances under which the classical approximation works. I'll come back to that when we do the cosmology story. But in the example that we've been looking at, this thing involving the complex scalar field, you know, all these scales v, m, and mu are all the same. There's only one scale m. They're all the same. And so if we specialize to that case, this is what we would have had for the particular theory that we were dealing with there. And this is doing, you know, we also had the property that every light field had to be differentiated because we had the symmetry where it shifts under a constant. And so that means that the number of derivatives has to be at least as big as, or bigger than, or the same as the number of fields. You never have any fields that are not differentiated. And we only could have, we had to have at least 4 fields in the interactions we found because the 1 over m squared terms were all redundant. So that the first interaction started at 1 over m to the 4th. And so that had 4 fields in it. So if we take this and we ask, what's the dominant contribution to the scattering of light particles at any order, we can decide. If we take E to be 4, that would be the light particle scattering. Then we could ask what makes the answer as big as possible. We want to pay the price of Q over M as few times as possible. So the first thing we'll do is take L equals 0. And the second thing we'll do is we'll ask this thing to be as small as possible. So that means that we can keep as many interactions as we like as long as they only have 2 derivatives in them. That'll be the minimum price we have to pay on this side. But we don't have any interactions with only 2 derivatives because we have to have at least 4 derivatives. So that means that the leading thing will be we'll take the minimum derivatives we have, but we'll work at the tree level where L is equal to 0. And that, in that case, will give us the answer that we already found, that A was Q over M to the 4th. But if you wondered, were there other graphs I should have drawn that I did not include that would have contributed to the same size as the ones that I did include in the effective theory? This is how you know that they're not there. But it also tells you, if you wanted to do the corrections, what are the leading corrections to the calculations we did? This tells you exactly which graphs you have to draw, which effective interactions you have to include. It's all very, very precise. And the farther you go down the low energy approximation, the more terms you include, the more complicated it gets and the more terms you have to include. But there's always a finite number of terms. And so it's always predictive in the low energy sense. And so we'll be using these formulas for gravity in explicit detail in cosmology, because they quantify what the small things are in the answers.
5 minutes left.
Yes. So I've got myself, you said 5 minutes left. So I've got myself at my timer is going to go off in 2 minutes. So is that 5 minutes at the end of the 75 minutes, or does that also leave time for questions?
And this may be something naive question. While describing the effective field theory Lagrangian, what's going on about the symmetry? Is it conserved or changed?
Is it, sorry, what was the last part? Is it what?
Is it conserved or changed?
Oh, so in everything I told you in this previous slide, this is agnostic in the sense that the symmetry, where I learn about the symmetry is in this statement here, that the fact that I told you that the number of derivatives has to be bigger than the number of fields is because the symmetry would imply that. The symmetry says that the fields have to appear differentiated. And then there's a minimum number of fields you need in the interactions. And Lorentz invariance forbids you from making something with 3 fields, given you have to differentiate them all, so you have to have 4. But you could have equally well done this whole power counting story without assuming the symmetry was there. And that would just change, you no longer would know that this was true, but you'd still know that this is true. And so the case of the symmetry or whether the symmetry is conserved or not is a choice you make. And the power counting in either case will tell you what are the biggest contributions in that case. And if the symmetry had been broken, you would have contributions here coming from the scalar potential. And those are actually important at low energies in a way that I'm going to say more about when we talk about cosmology. I was going to not mention it now, but it's true that the scalar potential is dangerous. Non-derivative interactions are dangerous at low energies for scalars.
Thank you.
The reason I was asking about time is, so right now it's, what I have here is 9:28. I see that we're, the 75 minutes is almost over, right? So that's including the question period. So this is probably a good place to stop. So this also gives me an idea how fast I'm going. And so it's, I can see that I'm going to shuffle the slides a little bit now. So in the grand scheme of things, there's only a couple things left in the effective field theory story. We're just about done. The main one was going to be this next topic, which I will not start now because we're almost out of time. But it's about whether it's important when you, in cosmology, we're going to have time-dependent background fields. And that sounds like that should be a problem for effective theories, because effective theories are being built on the assumption that energy is conserved, and we're using energy as a criterion to distinguish the low from the high energies. So it sounds like if you have a time-dependent background for which energy is not conserved because you've broken time translation invariance, it should be true that the effective theory is hard to apply. And the point of this section will be that it does apply, but it assumes that you're in the adiabatic limit. And so there is a sense in which effective theories can apply in time-dependent problems. And this toy example shows a nice concrete example of that, which I'll work through, which won't take very long. And then we'll switch to cosmology. So the most of tomorrow will be a review of cosmology, structure formation, and setting up, basically, I hope, the physics that we're going to be wanting to describe in the third lecture in terms of effective theory. So that's probably a good place to stop and take more questions.
Yes, thank you very much.
Thank you.
Any questions? Any questions from the Zoom audience?
I have a question on your talking about some normalizable couplings in the elliptic expansion. So in the higher dimension operators, you talked higher dimension operators to be suppressed by 1 over large M. But in quantum coupling, you said that it's proportional to small m. But
it's true. I did a notational a bad notational thing. So in the but you're right to flag it. So let me go back to that. I've forgotten now how I changed the slides here. Oh, here we go. So that what happened was when I was doing the original toy model, the only mass in the problem was little m. But when I switched to this effective theory, I started using capital M and little m as if they were. So if I go back to here, in this picture, I was imagining capital M was the heavy scale, and little m could have been a mass for somebody in your low energy theory. And so in the toy model example, the complex scalar field, little m would have been 0 because the light field was massless. But if we're doing something more general like quantum electrodynamics, for example, it might be true that the electron mass would be small m and the capital M might be the muon mass, which we might have integrated out. So at this point, little m is now playing the role of a mass in the low energy theory, which it was not playing in the original toy model I was starting off with. And that's confusing because I'm in the original toy model, the little m was playing the role of capital M in this later part of the lecture. If you see what I mean.
So my question is basically, what should be the natural questions of the, let's say just we have just a scalar theory with full scale m and large m, and we believe the higher dimensional operator should be suppressed by 1 over large m. What should be the coefficients of lambda phi cubic? G large m or G small m?
So you're asking about the coefficient of the cubic piece.
Yeah.
I think I understand the question. So you're saying that if I have a high dimension operator, I took large m to be the thing in the numerator, in the denominator. But if I have a cubic piece, then that mass is appearing in the numerator. Right. And so it's the special that's a special case of the question: what controls the if I have more than one scale at high energies, which scale is it that goes in the denominators and numerators? And what should happen? I was going to get to this on Wednesday, but what should happen is that if you imagine doing a loop of a particle of mass m, then it'll appear in the numerator and denominator. That mass m will be everywhere. That'll be on dimensional grounds what the answers depends on. So if you have a sum of loops which have involved different masses, you should imagine that the higher dimension terms are coming to you with a sum over all particles in the loop of 1 over mass of that particle. Whereas the cubic thing would come as sum over particles, all particles in the loop of the mass of the particle, say. And you can kind of see that in the higher dimensional operators where it's in the mass of the denominator, the smallest mass will win. Because if I sum over 1 over m of a whole bunch of different m's, the smallest mass will be the biggest term. Whereas if I do it in the cubic piece, it's the biggest mass that's going to win. And so the answer to your question is different for those two cases because the biggest mass that you did in the loop should be the one that appears in the numerator, whereas the smallest one that you integrated out should be the one that appears in the denominator. So if we had been doing the standard model, for example, and we were integrating out, let's say we integrated out from some physics where the standard model was the low energy theory, then let's say we had some physics at the Planck scale, and we had some physics at the intermediate scale, 10 to the 10 GeV, then in the non-normalizable interactions, it's the intermediate scale that would be the one that you expect in the higher dimension interactions. But if we had a low dimension interaction, like the cosmological constant or the Einstein term in the action that has a coefficient which is a positive power of mass, the biggest mass should appear there, and that should be the Planck mass, if you see what I mean.
Okay.
I'll be more explicit about that on Wednesday because that's part of the gravity story. Is that one of the successes of gravity is that having the Planck mass be so big makes a lot of sense because it's like the cubic term. It's in the numerator. Whereas having smaller masses in the higher dimension terms is something which people don't normally do, but it's actually true. If you look at string theory, for example, it's the string scale that goes in there, and the denominator is not the Planck scale. And so I'll make that distinction in more detail on Wednesday.
Okay, cool. Thank you.
Good question.
Okay. Any other questions? Any other questions from the Zoom audience? I don't see any more. So let's thank Cliff for the first lecture today. Thank you very much.
Thank you. We'll see you tomorrow.
Let's see you tomorrow.